This is a demonstration of the Milliohmmeter microtester. Microtesters are a family of dynamic instruments designed specifically for the semiconductor industry. Microtesters provide measurement capabilities and analytics that are not possible on static instruments. Microtesters collect a series of time domain measurements at programmable intervals. They then aggregate the measurements into statistics like average and sigma. Sigma serves as a quality of measurement metric, demonstrating that the measurement was accurate and low noise. Microtesters provide other analytics like frequency domain analysis, linearity statistics, and more. We will demonstrate these capabilities in this demo of the Milliohmmeter, which is part of the MCX Modular Dynamic Meter. The MCX architecture consists of single-channel dynamic instruments mounted onto a motherboard. We can configure the MCX in any number of channels with any of our dynamic instruments. This is a single-channel dynamic Milliohmmeter module. It mounts onto the MCX motherboard. The modular architecture minimizes downtime in production. In the rare event that a module fails, you can quickly replace it and recalibrate the instrument. We can also configure the MCX as a board that fits into the backplane of a test system. This is a 40-channel board with 34 channels installed. Power supplies are on the top right. There is a communication module on the top left to accelerate communication. This shortens the time required to download programs into the microtester and the time required to upload the test results and measurement statistics. Here's a configuration that will be used in the demo. This demo board replaces the MCX motherboard. The demo board mates to a test board with various resistors. It also contains regulators to supply the voltages used by the Milliohmmeter. Additionally, it contains transfer standards for calibration and NIST traceability. We provide a graphical user interface to assist in generating tests. The GUI helps the user to optimize the settings to get the best results at maximum throughput for production test. Once the user is satisfied with the test settings, the GUI can output source code with the click of a mouse. The GUI outputs both C and Python API code to files. Then it's just a matter of copying and pasting the code into your test program. We also provide a programming manual and complete user examples so that you can develop your own routines. Let's begin the demo. The top left panel contains the parameters to be programmed into the Milliohmmeter. The demo board also includes a 1x8 multiplexer, which this panel refers to as the channel number. The Milliohmmeter has 3 modes of operation. It can measure resistance and voltage as a function of time. It can also perform a curve tracer function of current versus resistance or current versus voltage. This button performs the measurement. In production, the test program triggers the measurement. The results are displayed here, in measurement, sigma, and sigma normalized by measurement. We also provide a set of tools to display the measurement results graphically. This panel displays the statistical results of the test. We preloaded a series of tests to demonstrate the capabilities of the Milliohmmeter. We'll begin by measuring a 1 milliohm, 1% resistor. The Restore button loads the presets into the GUI tool. These are the parameters for the measurement. We are deliberately oversampling the measurement in order to demonstrate how quiet the Milliohmmeter is. This will add a lot of test time, so you would reduce this parameter for production test. The LEDs above the tabs indicate where the relevant data is contained for this measurement. This displays the raw data for the measurement over time. The resistor measures at 1.004 milliohms with a sigma value of 5 microohms. The sigma value of the samples is within 0.5% of the measured value. The histogram tool shows that we're getting a very clean measurement. The FFT shows a noise floor down at 130 dBV and a measurement down at negative 60 dBV. The milliohmmeter is very quiet in the lab and on the production floor. Let's measure another resistor. This is an 80 milliohm 1% resistor. The test parameters and results are also displayed in the log panel. You can save the log files for future analysis offline. Again, we're getting excellent test results. The histogram looks good. And we are also seeing the noise floor down at around negative 130 dBV. We believe that this is the noise floor for the instrument. We purchased resistors from different manufacturers for this demo. We found that one has very strange characteristics. We slowed down the sample rate to get a longer look in time. As you can see, the resistance changes over time. The histogram looks bad. So does the FFT for the measurement. So we slowed down the measurements even further to see where it settles. As you can see, the resistance just keeps changing over time. The histogram tool illustrates the problem. It appears to be thermal noise in the lower frequencies. Now we will look at the 10-volt reference chip on the demo board. Notice that we changed the measurement mode to volts. The current source is disabled. The raw data looks good. So does the histogram. And we're not seeing any frequently related noise or harmonics. Notice that the noise floor is now negative 100 dBV. Our noise floor is down at negative 130 dBV, so we know that we are measuring the noise floor of the voltage reference chip and not of the instrument. The measurement is excellent, as is the sigma value of 129 microvolts. Next, we'll look at the curve tracer function. Notice that we press the curve button. We program the current source to ramp from 100 milliamps to 400 milliamps. We will perform 30 measurements with 256 samples per measurement. We will be displaying the 1 milliohm resistor and displaying volts. The sample rate is set high in order to see any small distortions in the measurements. This is the resulting data. We can zoom in on the graph. The results look pretty linear. The sigma values for the measurements also look good. We're seeing a change in sigma values of about 1.23 microvolts to about 1.45 microvolts. Since the transfer function resembles a DAC, we ran DNL and INL analysis on the data. The DNL is at 31.4 microohms and INL is at 20.6 microohms. The instrument is very linear. This test also demonstrates the diagnostic capabilities of the milliohmmeter, which is capable of testing itself on the tester load board. Lastly, we'll perform a series of tests which each have different pre-programmed settings. This speeds up the process when you're trying to make a series of measurements on a single pin or make measurements on multiple device pins. The results are displayed in tabular form from an array. Let's take a look at how the milliohmmeter is used in production test. We're selecting the 1 milliohm resistor as a worst case scenario. For this demo, we're setting up the test with the GUI, which is slower, but in production, your test program would be calling the APIs directly or sending hardware triggers. Now we're going to look at the accuracy of the instrument in production. We set the sample size down to 1 sample. We're not going to see anything on the graphical displays because we only ran 1 sample. We're getting a measurement of 1.004 milliohms, which is 0.4% accuracy. And of course, there's no sigma value for 1 sample. Let's increase the sample size to 10 so that we can use the analytic tools. At first look, the histogram looks a little strange until we realize that 100% of the samples are within 4 microohms. We're still getting 0.4% accuracy at the sigma points. The microtester is an excellent solution for both engineering and production test. This concludes our demonstration of the dynamic milliohmmeter. Thank you very much for watching, and please visit www.microtesters.com to learn more.